Bueno, buen día a todos los que hablan español. Tenemos algunos invitados que solo hablan inglés, así que la presentación la voy a dar en inglés, pero en los comentarios dejé pineado un link a la misma presentación que dimos en la Ecoparty que está en español, por si la quieren mirar, y igual si tienen dudas me pueden preguntar en español. So now we will start with the presentation. As you have seen in the post, this goes about some vulnerabilities we found in an IP camera, a camera that is connected to the internet, and exploiting these vulnerabilities, an attacker can hijack the stream, as you can see in many movies from Hollywood. So the idea of the talk is to go through the research process. We will start with the motivation. First, I will introduce myself. My name is Octavio Gianatiempo. I'm a security researcher at Faraday, and all this research was done with Javier Aguinaldo. So this research started when Javier's camera stopped working, and his wife asked him to fix it. But instead, he brought the camera to the office, and instead of fixing it, we started reverse engineering it and looking for bugs. So Javier was inspired by these kind of scenes that you have seen in many movies where a bunch of people try to rob a bank, for example. Oh, the presentation. Sorry. There we go. So let's go a little bit back. So my name is Octavio, and all this research was done with Javier too. The motivation behind this research was that Javier's camera stopped working, and his wife asked him to fix it, but he brought it to the office instead, and we started reverse engineering it and looking for bugs. So Javier was inspired by these scenes that we have all seen in the movies, where a bunch of people is trying to rob a bank, for example, and in this team there's a hacker that has the task to control the cameras and to let the others go unnoticed. So when he brought the camera to the office, we started turning it down, and well, we didn't take many photos along the process, and this is all that there's left now of the camera. But this is the main board, and here you can see that it has a memory where it stores the firmware. It has some connectors to solder, and when you connect there, you can have there's an UART interface, and you can get a kind of console. There are other sockets to connect motors and lights, because this camera has pan and tilt and zoom. There's an SD card reader that you can use to save your pictures and videos recorded with the camera. And the thing is that this camera is run by a custom system on a chip. So we didn't have much information available about this. We started by hooking to the UART interface and looking at the boot process. And from there, we learned that the camera uses U-boot as a bootloader. And when it starts, it tries to update its firmware from the SD card. You can see that here. And you can press Ctrl-U to stop this boot process and enter the U-boot menu. Yes, please, if you have any questions, raise your hand and interrupt me at any moment. So if you don't interrupt this boot process, the bootloader will continue to verify the app and the kernel image. And after it's completed this verified process, it will print some information about this kernel. We can see here that the camera runs Linux, and the processor is an ARM processor. So after it unpacks the kernel, it will run a script called initrun.sh. And this script can also be interrupted by pressing the letter Q. But if you let it continue, you land on a restricted shell that has some commands to control the camera, but they are very limited. So as researchers, we would like to have a full shell on the camera to inspect all the processes that run the camera, the connections, and interact with it. So a way to get this would be to escape one of these commands to get to the shell that is beneath this program. But there's an easier way. We can use the first combination of keys, Control U, to stop the boot process and enter the U-boot menu. And here we can see, using this command printm, the kernel boot line. And in this line, we can see that the kernel starts by mounting a RAM file system. There's an option called rdinit, which lets you specify which binary will get executed when this RAM file system gets mounted. Normally, this binary is called init or Linux RC, but we can change it to bin sh. So now, if we let the camera boot, the boot process will get stuck in this RAM file system, but we will get a full shell. We have this script init.sh that will normally continue the boot process and start all the features of the camera. But as you remember, if we continue the boot process now, we will land on the restricted shell. So looking around this RAM file system, we found a file at EZVIZ that defined that the user, the terminal user, will get the restricted shell called PSH. So luckily for us, the camera has bin, and we can use that to change this file and replace PSH with SH. And if we do that and continue the boot process, then the camera will mount all the other file systems, and we'll get a full functioning camera, but with a full shell on the UART interface. With the shell, we can start to look at the connections that the camera makes. You can see here that there are lots of sockets open. And one thing to notice is that all of these depend on a single binary called EZVIZ. So also, normally the camera is controlled by a cell phone app, and the camera and the cell phone app talk to each other using a cloud instance. And there you have the IP of the cloud instance in AWS. We didn't look at any of that. We focused on the firmware, but if you want to look around, there's it. And well, so this huge binary EZVIZ that controls all the features of the camera will be our main target. So with that in mind, we started analyzing the firmware, but we didn't have the firmware. So, and the firmware wasn't available on the vendor's website. So the strategy that we used to get the firmware of this camera was to intercept an update. We triggered an update from the cell phone application, and we listened to the network packets going by, and we found an endpoint that allows the camera to fetch updates from the server, from the EZVIZ server. So this endpoint has, in the URL, you have the model of the camera, and with that, we could download the firmware from this particular one. When we extracted it using binwalk, we found that this EZVIZ binary had no symbols, and this makes the reverse engineering process really hard. But since we had the endpoint and we knew other product names, we started forcing this endpoint to look for firmwares that had symbols. And luckily, we found one that it had. So we used bindiff to match the functions from the binary that had symbols to our version. And the first thing we noticed, and it got our attention, it was that this camera, that its brand is EZVIZ, had a lot of strings referencing to Hikvision, that at that moment we thought it was another brand. We started tracing these strings and looking at their origin and their uses, and we found that this camera implemented two Hikvision protocols. One called Search Active Device Protocol, which is SadProtocol, the protocol that this talk is centered on, and the other is called SDK Command Server. When we asked EZVIZ about this, they said that they are two separate companies, but it's really odd for a company to implement a protocol, a private protocol from another company. Around that time, there was a ban from the FCC in the US that prohibited all various brands, various Chinese brands, from being used on government agencies. So Hikvision was one of these brands. So this was an extra motivation for us to look at these protocols. The SAT protocol uses multicast and UDP and runs on port 37020, and it's controlled by EZVIZ. It's not documented, it's proprietary, and underneath it uses XML. Normally, you would use a desktop app from Hikvision using this protocol to activate your camera to configure the network settings and other features. This is what the application looks like, and this is a Hikvision application, but you can use it to control EZVIZ cameras, of course, because they implement this protocol. Normally, this application broadcasts a packet that has XML inside. It has different types of packets, and it always starts with an inquiry packet. When it broadcasts an inquiry packet, all the cameras in the network will respond with a matching packet that has a description of many settings and the firmware version and many versions. And well, this protocol can also be used to modify some camera settings, particularly some network settings, and it has a little bit more obscure part that use part of the Ethernet frame for communication. There's a great post reverse engineering that you can find right here, but we'll focus on the XML part. On the other hand, the SDK command server runs on TCP and listens on port 8000. It's also controlled by the EC app. It's also proprietary and not documented, but it's binary. It's a binary protocol. And the idea is that an advanced user can use C or C# alongside the Hikvision SDK to control the cameras, and this is used to control the playback, the view or to download files from the camera, and to control the motors to pan and tilt the camera. So now we have our attack surface, and we would like to find vulnerabilities affecting these protocols. For this, we used an approach that we have used before in a previous talk, and it's very simple. It's to find calls to vulnerable or potentially insecure functions from libc, like string copy or memcopy, and to check if the destination points to a stack. The idea is to try to find stack buffer overflows. Okay? So low-hanging fruit here. And going through the list of insecure calls, we filtered to find good candidates for remote code execution that were in functions related to these Hikvision protocols. And we found 2 stack buffer overflows in an SDK function handler. Unfortunately, these vulnerabilities are post-out. It means that the user or the attacker has to know the credentials for the camera to exploit them. But we also found 2 stack buffer overflows affecting the SAT protocol, in particular the packet parsing part of the protocol, and these are pre-authenticated. So now we will see a little bit about these bones. So the first 2, the ones that affect the SAT protocol, are in a function that is responsible for parsing the XML in the packets. As you might recall, the protocol starts by asking all the cameras to identify themselves, but then you can use this protocol to configure a particular camera. And when you want to talk to a particular camera, since you are broadcasting your message, you have to include a tag that has the MAC address of the camera you want to control. And I think, yeah. So this is a very big function, but it comes to a part when it will compare the tag to the keyword MAC. And if it finds this tag, then it will copy the content of the tag with its full length to a buffer on the stack without controlling the size. This buffer has a fixed size. So this is the buffer up here. This has 64 bytes, and you can put a MAC address as long as you want inside the tag. So when this gets called, you have a stack buffer overflow. Then the function makes a copy of this buffer. I still don't know why it does this, but it does. And after that, it passes this buffer that contains the MAC address, which is unparsed yet, to this function called convertMAC, that it will try to parse this MAC address and convert it to a number. So convertMAC has 2 arguments, a destination buffer and a source buffer. And it maintains 2 indexes which we'll use to point to these buffers. The source buffer contains a MAC address, supposedly. So the function will check if the character that's looking at is a separation character for a MAC address, which can be a hyphen, a colon, or a space. And if it finds one, it will advance the indices and write a 0. However, if the character is not a separator character, it will convert from hex that number to a decimal number and will store it on the destination buffer. So if you see here, there's no check about how many separator characters you can have. Normally, a MAC address has 6 octets and 5 separator characters, but if you send more than 5 characters, then these indexes will keep on advancing and you can write outside the original destination buffer, resulting in another stack buffer overflow. So the other vulnerabilities that are part of the SDK protocol are much simpler. There's a function that is responsible of setting some wireless configurations. And I won't get into much detail, but depending on the security type that the network has, it will end up copying one way or another the key into a buffer on the stack, also resulting on a stack buffer overflow. So now we have found some bugs on our attack surface. And for example, for the SadP1, if we send a long enough MAC address, the camera will crash. So if we want to develop an exploit for an embedded device, we would like to inspect the side effects of our crash. We would like to know which registers are affected and which memory locations are affected too. And this will allow us to find the right offsets for exploitation. And if our binary that we're trying to exploit has some mitigations, well, we will try to bypass those mitigations. And to do this, it will be great to have a debugger running on the camera. But for that, you have to compile it first. Also, sometimes you find something like potentially vulnerable place in the code, and all you have is a chain of function calls from an entry point, for example, socket or a web endpoint, and you can follow those calls into a piece of code that you think is vulnerable. But when you try to trigger it, you fail. You go to look into the binary, and maybe you don't have symbols, there are no strings, you don't know much about the code. So in this scenario, a debugger would also be of great help. The first thing to keep in mind is that to compile a binary that will run on the camera, you have to know the kernel and GCC versions. But if you had a shell before on the device, this is really simple. You have to just cut these special files in Linux, and you will get that information. And with that, the simplest approach is to try to find a Docker image from a distribution that has a kernel and GCC version similar to the one you found on your embedded device. If you compile a binary using this image, you won't have the same libc implementation that is running on the camera, because usually these embedded devices use specialized libcs. But you can always compile your binary statically, and in most cases, this will work, and the binary you compile will run on the camera. For example, you would like to compile a GDB server to debug your exploit. But well, sometimes this approach is not enough. In the case of this camera, for example, the space was really limited, and when we tried to write a static binary into the file system, it crashed. So we had to make a full toolchain. And the idea behind the full toolchain is that you construct an environment using, for example, crosstool or buildroot, that has all the versions, the same versions of the kernel, but also from the libraries that your embedded device is using. And with that, you can compile a binary that uses the libraries that are already on your embedded device. So its size would be way, way smaller. So now we had a debugger on the camera and a crash, and we'd like to make an exploit. But this binary, the EZVIZ, has some mitigations. Its stack is not executable. It has no PI, so it gets always loaded on the same base address. But as you can see right here, this address has some zeros in it, so it will have some null values when you send this. And remember that we will be sending our payload on an XML structure. So if we send some null bytes, the XML will end early, and it will be rejected by the parser because it won't find the closing tag of the part of the XML where you put your null byte. So we can send null bytes on our payload. And since our address space of the binary has null bytes, we cannot target pieces of code that lie on the binary. On the other hand, the system has ASLR, so the addresses of the libraries is randomized. Each time this binary is loaded by the camera, the binary itself is on the same address, but the libraries will change. So for successful exploitation strategy, we need a leak. We need to know where these libraries get loaded in order to jump to them and to build our route chain. So how can we turn this overflow into a leak? Using this debugger that we loaded into the camera, we stepped carefully through the function that is vulnerable and also through the calling function. So when the vulnerable function ends, it ends with this instruction, pop R4 to R11. It means that when we overflow the stack, we can control registers from 4 to 11. Also, we can control the program counter. After this function returns, the calling function calls this instruction, store the contents of register 4 into the address pointed by R5 and R3. So if with our overflow, we override the addresses on the stack that will be used to load the values of these registers, but we leave the program counter untouched, when we return to the calling function, we'll have an arbitrary write because we can specify the content in this register, R4, and we can specify the direction using both these registers. So what can we write with this primitive, with this arbitrary write primitive to leak addresses? Well, this camera has the real-time stream protocol. That is a protocol used to negotiate video and audio streaming between a server and a client. And this protocol resembles a bit to HTTP in the fact that we have some verbs that the client sends to the server, and the server will respond to a code with the code. For example, here we are asking the server to describe all the streams that it has, and since this server requires authentication, it will respond for one you are authorized to watch these streams. If we look at the binary, there's a table that has an array of structs with pointers to these status codes. For example, here is 401, and a pointer to the message unauthorized. On the other hand, on our binary, since it's an F binary, we have the global address table, which is a table that contains, in runtime, all the pointers to the functions in these libraries, because since these libraries will change its address with each execution, the loader has to complete these addresses on runtime. So what happens if we can control and write an address that points to the global offset table in this array of responses? Well, now when we talk to the server, instead of a response code, it will send us addresses from the global offset table. And we can parse these addresses to know the actual addresses of the functions. In turn, this will be used by us to find payloads, to find gadgets to build our route chain. So the strategy is the following. Find a gadget to copy a string from the stack, that we control the string in the stack because we can send it inside the XML packet, and copy it to a known empty location. Then call system to execute this string as a command. And after that, we have to call the thread exit. And this is to cause the SadProtocol thread to terminate without crashing. Remember that all the functions of the camera, all the features, are run by this EZ app. And this EZ app has a thread for each of these functions. So if, for example, you send your exploit and the thread that controls the SadProtocol server crashes, then all the binary will crash. And for a POC, that doesn't matter much. But if you want to do a real exploit, you wouldn't want the victim to notice that their camera had stopped working. So if you call Peter exit, the SadProtocol server will terminate, but all the other functionalities of the camera will continue working. And the command that we choose to execute with system is a call to a TFTP camera, to a TFTP client that the camera has. And we use this client to fetch a binary, an attack control binary from an attack control server, and then execute it. So when making these slides, we realized that ConvertMac can also be used for exploitation. And the thing about ConvertMac is that it will, for example, you can send in the XML this MAC. It's not a valid MAC, but it doesn't matter. And this MAC will get copied, and a null byte will be added at the end. So when this buffer gets to ConvertMac, what will happen is that all these hyphens will advance these indexes that ConvertMac uses internally, and it will get to the point of the return address in stack. So now these values that we control will get written to the stack from the return address, and we can write 3 more. Unfortunately, this is not enough to build a good prop chain, but we realized that when ConvertMac finds a separated character, it not only does advance these indexes, but also writes a null. So we can set something like this. This will get copied, and it will result in this written on the stack. So now we will use hyphens to encode null values on our addresses. For example, these 2 characters will result in 2 null bytes. Before, we needed you to use 2 zeros to encode a null. And with this strategy, we only need 1 hyphen to encode a null. So this allowed us to control 4 addresses apart from the return address. And with this, we can build a rob chain that goes to system, but with a pointer to the SadP buffer pointer. Sadly, there's not enough space to add a gadget that calls pthread exit, so this will make the program crash. But nevertheless, you will get execution and very reliable. So this SadP buffer pointer is no other than the pointer to the buffer that contains the XML. And thus you can insert your command at the start of the XML and comment the rest. So let's see some videos of this in action. On the right, you have the UART output of the camera that now it is booting. On the left, you have the attacker terminal. The camera takes some time to boot. Here we can see a binary that the attacker will push to the camera using TFTP. It only prints 1 by Faraday. And the attacker will start this TFTP server. And then we'll wait to the camera to finish booting to send the exploit. So I will pause just a little bit here because it's weak, but here you can see that after we use our arbitrary right to override the response table from RTSP, we send a request to the RTSP server, and it responds with the leaked addresses. With that, we can calculate the gadget that we would like to use, we build our wrap chain, and our wrap chain is now inserted in the MAC into the MAC tag of the protocol. This causes the camera to fetch the binary called X from the TFTP server that is controlled by the attacker and execute it. This is the other approach, the one that uses convert MAC, that it will cause the camera to crash, but it's much more reliable because in just one step, you send a command to system and you will get remote code execution. So the idea is the same, but we don't have to leak any addresses here. We can jump to addresses on the binary because we can write null bytes using convert MAC. Okay. Sorry. So now we have a working exploit that allowed us to achieve remote code execution in our camera, but we still have to implement Javier's idea to do Hollywood-style post-exploitation. So we would like to control the camera stream without the victim knowing. Our first idea was to modify the video frames in memory, but it was too hard. And then it occurred to us to modify the RTSP response from the server because the client and the server use RTSP to negotiate the channels for communication for streaming, for audio and video streaming. And if you modify that, then the RTSP protocol could tell the client to connect to other address to fetch the stream, but this wouldn't be transparent for the client. The client or the victim would notice that they are connecting to an attacker-controlled server, and also it didn't work. So we decided to use it to null. But we have this problem. As I told you before, EZVIZ controls every feature of the camera, and its features runs on a thread. In particular, RTSP is already running. And to tunnel the victim into attacker-controlled server, we want to use that port. So now, apart from not crashing the binary, we have to shut down RTSP cleanly. So the general exploitation approach is to fetch an executable with TFTP, and as we did before, and this executable will instrument EZVIZ using the ptrace syscall. This binary will use that to terminate the RTSP thread, and then we'll fetch another binary, the tunnel, and create a tunnel between the camera and the attacker-controlled server. So this is our binary. It starts by using ptrace to attach to the EZVIZ binary that is already running. And if you do this, you will get attached to a thread. So the thread is running and is responsible of some functionality of the camera. And we would like to save the execution state for that functionality to continue working after we execute this part of the exploit. So we save all the registers and execution context, and then look in the EZVIZ memory for an object that represents the RTSP server, and that it has a method that will make this server end cleanly and release all the resources that it uses. So we will look for this object, and then we will call its destroyer. And after that, we have to restore the registers to continue this thread normally. When we do that, we can then move on to the next step of the attack, fetch the tunnel using TFTP, and establish the tunnel between the normal port 554, which is the normal port for RTSP, so the victim doesn't notice that it's connecting to an attacker control server, which runs on a different IP and another port. So we used an open implementation of a normal tunnel, and just some drawings to clarify. So the victim will connect to the camera as it does normally, but the camera internally will forward this traffic to an attacker-controlled RTSP server. So the fun part, the demo. Now the camera has already booted, and the victim can connect to it using RTSP. And as normally, it will get a live feed from the camera. Now the attacker sends the exploit. I will pause it just there. The first stage of the exploit then attaches to the EZVIZ binary. It looks for this RTSP server object, and it executes this structure and releases its resources. So now the RTSP server from the camera is not working, and the port is free. And the exploit continues to fetch the tunnel and establish this tunnel. From the attacker part, the attacker starts its own RTSP server. And now, when the victim connects to the camera, it will get through the tunnel. So after the fun proof of concept, some takeaways. The whole idea behind this research was to question the integrity of video surveillance systems. And we all know that memory corruption vulnerabilities abound on embedded and IoT devices. The thing is that they also abound on the ones that are marketed as security products, like these IP cameras. And the other thing to reflect on is that these kind of vulnerabilities can be easily detected by static analysis and reduced by implementing secure development practices. These practices are standard in other industries now, and this shows that methodologies in embedded and IoT devices have a gap with respect to other industries. And this shows that security is not a priority for vendors, even when they manufacture security-related products. So I hope you liked the presentation and the POC, and if you have any questions, just ask. Sí, Robert, a ver.
Sí, una pregunta. Digamos, SadProtocol, ¿no? También, ¿sabés si los usan los timbres eléctricos de los porteros que usan Wi-Fi, digamos, los que se cargan en Android? Porque, digamos, Android carga la cámara en un WebView, ¿no? Digamos, y es como un navegador. Entonces, la pregunta es, SadProtocol, ¿sabés si funciona, por ejemplo, en los timbres Bluetooth que se cargan la vista desde Android, digamos? ¿Se entiende la pregunta?
Sí, se entiende. O sea, SadProtocol es un protocolo de Hikvision.
Ok.
Y está en los productos Hikvision. Si esos
Hikvision
timbres son de esa marca, quizás lo tenga. Habría que ver.
Y la pregunta, ok, entonces, una nueva pregunta. Por ejemplo, ¿sabés si las marcas de otras cámaras usan protocolos similares? ¿O difieren mucho?
No lo sé, o sea, el tema de este protocolo es, de alguna forma vos tenés que poder conectarte a tu cámara la primera vez que la enchufas en la red, ¿no?
Ok.
La forma que tiene Hikvision de hacerlo es esto, ¿no? Mandar un paquete broadcast y que la cámara conteste sola.
Ok.
Otros hacen que la cámara levante un endpoint Wi-Fi, por ejemplo. Que vos te conectes al Wi-Fi de la cámara primero y después la enlaces, ¿no?
Ok, esa es la... Ok, gracias.
Depende de la metodología de la marca.
Sí, claro.
O sea, es como algo muy particular de Hikvision.
Claro, sí, por eso. Quería saber qué tan particular, o sea, es de Hikvision o si es, digamos, el resto de las cámaras funcionan de una forma bastante similar. No te decía, pero, digamos, puede diferir bastante, digamos. Esa es la...
Sí, sí, es algo bastante particular y bastante raro.
Listo, gracias.
¿Alguna otra pregunta? Any other question?
Yo tengo una.
Sí, Rodrigo.
Una vez que ustedes realizan esto, ¿cuál sería la siguiente etapa? ¿Le avisan ¿cómo se dice?
Sí,
A la empresa?
sí, exactamente. Nosotros reportamos las vulnerabilidades a la marca y esperamos que la marca las arregle antes de dar la charla. Para el momento que damos la charla, las vulnerabilidades ya están arregladas. Sí, si es que la marca contesta, ¿no? A veces puede pasar que nunca contesten, pero
Claro, pero
general,
por ahí lo que me queda la duda, o sea, uno le dice a la marca, esto está fallando, pero depende después quién, tipo, la marca tiene que hacerse cargo, una onda así, de a todos los que le vendió para...
sí, por ejemplo, en el caso de estas cámaras, se pueden actualizar de forma automática. La cámara está todo el tiempo preguntando si hay un update disponible. Entonces, en el momento en que la marca saca un nuevo firmware que ya está parcheado, todas las cámaras afectadas bajan el firmware nuevo. Salvo que la persona explícitamente le diga no te actualices, pero si no, por defecto se actualiza.
Yo, esa es una, y después anoté, tenía una pregunta por ahí medio básica, pero usaste Blink y el otro Hydra, son las dos herramientas que usas para esto. Y ¿puede ser?
Sí, usamos mucho Hydra, ahora estamos empezando a usar Binary Ninja también. Pero sí, esas son las herramientas que hacen la parte de ingeniería inversa, ¿no? Que pasan del binario y te generan una especie de pseudocódigo que es más fácil de auditar y de buscar vulnerabilidades.
Ah, está, eso era, gracias.
Gracias. Bueno, ¿alguna otra pregunta? Any other question? Bueno, muchas gracias a todos por venir.